Today we are going to discuss the acceleration analysis of a 4-bar mechanism. So the question is, in a 4-link mechanism, the crank AB rotates at 36 radians per second. The length of the links are AB is equal to 200 mm, BC is equal to 400 mm, CD is equal to 450 mm, and AD is equal to 600 mm. AD is the fixed link, and at the instant when the AB is at right angle to AD, determine the velocity and acceleration at the midpoint of the link BC. Okay, so we have already deal with the same question with velocity only. So today we are going to extend that particular question up to acceleration, how to find the acceleration of that particular question. Okay, so before that, I would like to tell you something related to acceleration analysis. Every acceleration vector is actually a resultant of two components. Okay, so suppose this is the acceleration vector, then the acceleration vector is actually the resultant of two components which are of mutually perpendicular in direction. Okay, each acceleration vector is a resultant of two components which are of mutually perpendicular in direction. Okay, so the first component is tangential component, and the second component is centripetal component. Okay, so what is tangential component and what is centripetal component? So consider a link like this. So OA is a link for an example. So here the acceleration which is tangent to the link like this is the component actually tangential component. This component is tangential component. Okay, tangential component. And the acceleration which is along the link, towards the fixed point. So here O is the fixed point, so towards the fixed point, so the direction will be like this. Okay, so direction of the vector will be towards the fixed point. Okay, so this will be the direction of the centripetal component. Okay, centripetal component, and this is the tangential component. Okay, so the acceleration vector will be the resultant of both these two components. Okay, while dealing with the velocity analysis, we have to draw only the velocity vectors. So here in the acceleration analysis, we have to draw the component vectors. From that component vectors, we have to draw the acceleration vector. So next, the values of tangential component and centripetal component. So what is the value of tangential component? So tangential component is given by r alpha Tc. Okay, then where r is the length of the link and alpha is the angular acceleration. Then centripetal acceleration, that is Cc, is given by v square by r. Okay, v square by r. Let us see the question. AB, BC, CD and DA. Okay, and AB is equal to 200 mm, BC is of 400 mm, CD is of 450 mm, AD is of 600 mm, and AB is rotating in a clockwise direction with an angular velocity of 36 radians per second. Okay, so here from the question we can see that the angular acceleration for the link is not given. Okay, the angular acceleration alpha value is not given. So first of all, we have to draw the velocity diagram. How to draw the velocity diagram is already explained in my previous videos, so please refer to that. And now I am continuing with the acceleration analysis. So the name of the link is AB, BC, CD and DA, and finally we have to find the velocity and an acceleration of the point E. Okay, so the length is given by 0.2 meter. So here I am using meter, relative velocity meter per second, scale velocity in mm, then relative acceleration in meter per second square, then scaled acceleration I am using the scale as dimension as centimeter. Okay, so 0.2 meter, 0.4 meter, 0.45 meter, then this is 0.6 meter. So from the velocity diagram, VBA, velocity of B with respect to A, it is 7.2 meter per second, and the scaled velocity while I am drawing it was 72. Then VCB, velocity of C with respect to B, it is actually 3.96, 39 mm approximately. Then VCD, velocity of C with respect to D, it was 6.6 meter per second. 66 was the measured dimension, and the velocity is of 6.5. 65.55 mm was the dimension measured from the velocity diagram. Okay, so now let us move to the acceleration diagram. Okay, so all these values have to be completed before drawing this acceleration diagram. Okay, we are starting the acceleration analysis. Okay, so for that, first of all we have to mark the fixed points. Okay, so here you can see that A and D are the fixed points, so I am marking it as A comma D. A comma D, let it be a dash here. A dash, D dash. I am using a dash notation because here I am using A, D. Okay, so in order to find a difference between the velocity diagram and the acceleration diagram, I am using a dash nomenclature for the acceleration diagram. Okay, so A dash, D dash. Okay, so now next we have to draw the relative acceleration diagram. So for that we need a tangential component, a centripetal component, and finally the resultant. Okay, resultant, which is acceleration of B with respect to A. Okay, acceleration of B with respect to A. So first of all, what is the tangential component? We know that the value of tangential component is given by R alpha, right? So here from the question, the alpha value is not given. It means that it is having a uniform velocity, so there is no change in velocity. Okay, so the velocity is not changing, so there will not be any acceleration. Okay, so here this component vector will be 0. This component vector is 0. Okay, so I am taking this component vector as 0. Next is centripetal component, CC. Okay, so the centripetal component is V square by R. Okay, so V square by R. So next I am calculating the value of V square by R. So where V is equal to 7.2 meter per second, so which implies 7.2 square divided by 0.2, and the value will be equal to 259.2 meter per second square. Okay, so I am writing this value 259.2 meter per second square, and I am taking this value as 5 centimeter for drawing the acceleration diagram. Okay, next is the direction. So I have told that the direction of the centripetal component will be parallel to the link, and the value will be equal to 259.2 meter per second square, and the direction will be like this. Okay, direction will be like this. That means towards the fixed point. So here A is the fixed point. So towards the fixed point will be the direction of the centripetal component of the link AB. Okay, now I am going to draw the centripetal component. Okay, so the centripetal component, I'm just drawing the centripetal component. Okay, so this is the centripetal component. So if in some question there is a possibility of providing the angular acceleration value, so in that particular case we have to calculate the tangential component value, that means R alpha. Okay, and that tangential component has to be drawn over here as the second vector, which is perpendicular to this direction. Okay, perpendicular to this component. Okay, if it is in anti-clockwise direction, this will be the direction. If it is in clockwise direction, then it will be in the opposite direction. Okay, so leave that. So after drawing this centripetal component and tangential component, we have to draw the acceleration vector. Okay, so this will be the acceleration vector in the case if you have provided with the angular acceleration value. Okay, with an angular acceleration value, suppose an angular acceleration of x value in a anti-clockwise direction, this will be the initial vector. Okay, so here in this question we are not provided with the angular acceleration for the link AB, okay, which is the crank. So in this case we have only got the centripetal component. So the resultant of a centripetal component and tangential component, here the tangential vector is 0. Okay, so the resultant will be same as the centripetal component. Okay, centripetal component same as the centripetal component. Okay, so this will be the point B dash. Okay, so this will be the point B dash. Okay, so next you have to draw the centripetal component of the link BC from the point B dash. Okay, so the value of B dash, so I am going to draw the link BC. So for that, so I have to calculate the centripetal component, which is V square by R. So here the V square by R value, V square, so what is the value of V? It is 3.96 square divided by 0.4, and which will be equal to 39.204. So I am writing this as here also TC, CC, and the resultant acceleration A dash of C with respect to B. Okay, A dash CB, well, acceleration of C with respect to B. So the value of centripetal component is 39.204. 39.204. Okay, 204. And by taking the ratio, the corresponding component for this scale drawing for the acceleration diagram will be equal to 0.786. Okay, 0.786. By taking the ratio, simply take the ratio, so you can get the value of the dimension for the acceleration diagram. Okay, so next we have to determine the direction of this. So here the point B is assumed to be fixed. Okay, so in this link BC, we are taking the relative acceleration. That means the acceleration of C with respect to B. Here B is assumed to be fixed. Okay, so then the direction of the centripetal component will be like this, towards the fixed point. So here B is the fixed point. So towards the fixed point will be the direction of the centripetal component. Okay, so here 0.786 is the dimension. Okay, so this much of dimension will be 0.786, and this is actually the centripetal component. Okay, so next I know that the tangential component is perpendicular to the centripetal component, right? So I am just drawing a perpendicular dotted line. Okay, and this will be the tangential component of acceleration of CB, and this is the centripetal component of acceleration of A dash CB. Okay, next what we are going to do is plot the centripetal component of the link CD. Okay, centripetal component of the link CD. So here also we are going to determine the centripetal component, and finally the resultant A dash C with respect to D. That means the acceleration of C with respect to D. So next we have to calculate the value of centripetal component of link CD. So link CD, centripetal component of link CD, V square by R. This value will be from the velocity diagram. That means 6.6 square divided by 0.45, and will be equal to 96.8 meter per second square. Okay, so I am writing the value as 96.8 meter per second square. Similarly, by taking the ratio with respect to 259.2, the value corresponding to the acceleration diagram will be equal to 1.867 centimeter. Okay, 1.867 centimeter. So next we have to determine the direction. So here D is the fixed point. So the component vector, that means the centripetal component vector, will be having a direction like this. Okay, so towards the fixed point. Okay, so and the D point is here, the point D is over here, and towards the fixed point, I think it will be like this. Okay, and this much of dimension will be, this much of dimension is equal to 1.876 centimeter, and this value will be corresponding to centripetal component of A dash CD, acceleration component of C with respect to D, centripetal component of acceleration. Okay, so next from this point I have to draw a perpendicular. Okay, I have to draw a perpendicular which is the tangential component. So this will be the tangential component of acceleration of C with respect to D. Okay, so this vector and this vector will meet a common point. Okay, this intersection point is C dash. And the vector joining this point B dash C dash. Okay, the vector joining this point B dash C dash will be the acceleration vector A dash C B. Okay, acceleration vector or acceleration of C with respect to B. So here the direction is like this and the direction is like this for this tangential component. Okay, so now we have got the point C dash, and next we are going to draw the acceleration vector CD, A dash CD. Okay, so A dash is here, D dash is here and C dash is here. So just join these two lines. Okay, and the direction of the vector will be like this. Okay, so now we have completed the acceleration diagram. Next we have to locate the point E. Which is at the center, exactly middle of this acceleration diagram. Okay, either you can bisect this line or take the ratio of BC as we have done in the velocity diagram. Okay, so take the length BC divided by BE is equal to acceleration of CB divided by acceleration of BE. So this is the point E. Okay, so after obtaining this point E, you have to join the point E with the D or the grounded points. Then only we will be able to measure the actual or absolute acceleration. Okay, the absolute acceleration of the point E. It will be obtained by joining this point, fixed point A dash D dash with E dash. Okay, this is the point E dash. Okay, so I am just drawing this line. Okay, and this is the vector. This black color vector is actually the result. Okay, upon measuring this particular dimension, we can find that the value will be equal to 4.25. Okay, 4.25 centimeter. And similarly, by taking the ratio to 59.2 divided by x is equal to 5 divided by 4.25, you will be getting the value as 220.32. Okay, 220.32 as the acceleration of E. That means it is actually the resultant acceleration of E with respect to A or D. That means the grounded point. Okay, so this is how we are going to draw the acceleration analysis. Okay, so let me explain the procedure once again. So first of all, read the question well. So first of all, draw the configuration diagram, then construct the velocity diagram. After that, you have to draw the acceleration diagram. Okay, so for drawing the acceleration diagram, first you have to mark the fixed points. Okay. Then first draw the centripetal component. So this is, then draw this tangential component. Here the tangential component value is 0, so the resultant value will be equal to the centripetal component. Okay, so here you are drawing the centripetal component as the resultant. Okay, then from the point B you have to draw the second centripetal component. That means the centripetal component of the link BC. From there you have to draw the tangential component. Okay, so tangential component of the link BC. Then you have to draw the centripetal component of the link CD. Okay, centripetal component of the link CD. After that you have to draw the tangential component of the link CD. Vector or the lines 3 and 5 will meet at a common point called C dash. Okay, and that particular point will be C dash. Now join the vectors B dash and C dash. Okay, now join the vector B dash and C dash. So this will be the 6th vector and this will be the 7th vector. Okay, 7th vector, and finally this will be your 8th vector, which will give the absolute velocity, which will give the absolute acceleration value of the point E. Okay, so please try to do the question. Thank you.